Alright, I had a lot of questions and requests for additional discussion about this in-class supplemental exercise. So let's take a closer look here. We've got three cables. One that's this diagonal one at 50 degrees from the horizontal, a horizontal one, and then we have this third one that's wrapped around the pulley at the middle and then back down to the weight that we're trying to lift and back up to the pulley and tied off there. Right, so let's take a look at how we might begin to approach this. When I look at this system and just making this kind of gross weight without doing a lot of careful thought about it, I might say, well, alright, fine, I got this little weight down here and it's attached with some sort of rigid link up to the pulley, and so as I cut around this thing and make a free body diagram, I'm physically cutting two cables. They got to pull away from the weight, and I know here that this cable has a capacity equal to 100 pounds. The other two have larger capacities that are twice as much, and so let's assume DAE breaks first. Don't know if that's right or not, but that's what I'll assume. Because it's nice and simple, this is very clearly here, and I know this is applying our suite of statics, but it's a really simple one, and one that might be sort of intuitive for even people on the street here that don't have any background. We just do a really simple thing here to get to that, hey, T is equal to W over 2. Right? And if then T is equal to 100 pounds, its capacity, right, that breaks, then that means that W would be our guess of 200 pounds. So why not do an initial analysis associated with that? All right, so let's go do something a little bit more complete and sophisticated. So what calls out to be done is let's go do a free body diagram of our pulley A. And so let's get that drawn in here, and we need to be really quite careful about how we're doing this, right? And so we don't want to make up angles that don't actually exist. We don't want to make up things or make assumptions about things because it might cloud our judgment about what we think is really going on. So let's be really careful. Each cable or rope must be in tension, so pulling away from the free body. Right, this is the body that we've got. Tension means for AB it has to be directed to the left. If we do our work, we find out there's a minus sign, that means we've got it going the wrong direction. Also means we have a problem, Houston, because in that case the cable would be going into compression, and that's not going to work out so well. Right, so then there's TAC. Now some people want to say, well, then shouldn't each of them be at their capacity? No! There's nothing that suggests that all cables would break simultaneously. And that would be rare for something like that to ever happen. It's not the way reality would work. Right? Now we've cut through cable DAE 3 times, not twice, but 3 times, and let's show it in how it really works. Don't make assumptions here. Right? So that's our cable force from DAE going direct from the pulley down to the weight. And then the one that is coming back the other way around, people want to say, well, I'm following and drawing and going, and that means that arrow's going up. No! What did we remove from this body? We removed a cable that's pulling away from the free body because it's in tension. It has to be going down. Note, if we put this one and this one together, they would, of course, vectorially go to 0. So they are equal and opposite from the top and the bottom for that cable. Same thing with this one over here. Right, and then AD is coming down at 30 degrees from the vertical. It's also T because it's all the same cable, and we're not including friction. Right, so that's at 30 degrees from the vertical. TAC is 50 degrees from the horizontal. Now we could simplify this a little bit if we wanted to, and particularly what we can do here is we've got the horizontal to the left, TAB. We've got upwards to the right, TAC. And then we have 3 pieces of the DAE cable. So 1, 2, that would be T and T, and then we got this little 30 degrees here, right? So cosine of 30 equals 0.866, and of course cosine of 60 would equal 1/2. So that makes it a little bit easier here to just say right off the bat the vertical component that comes from this DAE cable is 2T plus 0.866T, right? 2T from these and then 0.866 from the inclined one. Wow, pulling down increases the effect here. That's kind of important. And we have a X component acting to the right, which is going to be at 1/2, so that's T over 2, which in itself we've already figured out from above is equal to W over 2, so that's going to be W over 4. Wow, that's pretty important here. Alright, now we can execute. Let's go sum forces in the Y. Take upwards is positive. TAC times the sine of 50 degrees is that Y component, and then minus 2.866 T, which is really W over 2, is equal to 0. So therefore, TAC equals then, let's see, 1.433 W divided by sine of 50 degrees. And 1.433 divided by 50 sine equals 1.87 W. Right? Now we already know that the limiting factor here is that the DAE, if it's set equal to 100, then W equals 200 pounds. But if W equals 200 pounds, well then TAC would equal a lot more, 374 pounds, and that's too big. That's greater than the 200 pounds that's the capacity of that. So that's no good. That tells me that DAE does not break first. Rather, AC breaks before DAE does. Right? So, But let's carry on this little investigation here, because this just gives us a ratio that has nothing to do with whether W is 200 or not. Right, so now let's go look at sum of forces in the X. Let's take to the left positive, and we get TAB, and then minus the X component of TAC, which is cosine of 50 degrees, and then we need the X component of T over 2, so that's again W over 4, set that equal to 0. So TAB then is going to be equal to 1.87 W times cosine 50 degrees plus W over 4. Oh wow, that's going to even be bigger. That's going to be 1.87 times 50 cosine equals that plus 0.25. Oh, well, that's interesting. 1.45 W. Right? I want to just verify that real quick. Right? So we've got TAC. TAC is equal to 1.87 W. And then we take it times 50 cosine, that's the X component, plus the 0.25, yep, 1.45. Okay? And so if W is 200, then that means TAB would be equal to 290 pounds. That's too large also. That would fail. Now, notice the one that fails first is going to be AC, right? Because as I start off at 0, and then I take it and make it 10 pounds of the weight, that is, then all of these increase. If I make this 20, they all double. If I make it 30, they all go up by some linear relationship. Right? So what we've actually figured out here is cable AC breaks first. So let's rescale all of our results. Okay? We know that it breaks, TAC would equal 200 pounds. And we know that when that's 200 pounds, what do we know? Well, we don't know a lot. We know if TAC is 374, we've applied a W of 200. So we need a lot less. So W over the 374, that's coming from W equals 200 pounds. That's our the beginning of our scaling factor. And then we need a 200 pound force in TAC. Right? So that's going to be 200 times 200 divided by 374. That's going to be 106.95 or 107 really pounds is going to be our W. You're probably saying at this point, what? How did you get there? All right, so the unfortunate part is we got too many things running around that look like the same numbers. Right, so we found out that TAC breaks first up here, right? And if W is 200 pounds, then we get 374 pounds in AC. We want to back off on all of this, rescale it down. That's the 200 over 374. The strength of TAC, the force of 374, that's our scaling factor, and that will tell us what is the new W that will give us that. So a new W of 107 will create a TAC cable force of 200 pounds. Right? And so that's why that's our answer, and why we don't have to check all the others. We already know they're going to be lower than their strength. Right? All right, so let's close that off.